It's really a pleasure to be back here and talk about, a bit on the hardware side of my research. And like Jill said, having seen Horizon grow, and this is really lovely to see the new office and the team growing. So, okay, let's get started. It's going to be a fairly general talk, kind of on the overview level of what we're doing on the hardware side and what are some of the challenges and maybe what some of the strategies for overcoming those challenges. Okay, in the end, I'll share a little bit about what we do at NUS right now and sort of where we are in building the team and the infrastructure. Okay, so to start with, I just want to go over very briefly this general overview of what it takes to actually build a quantum computer. And this is not specific to superconducting circuits, right? So here we see that, this is just a very naive way of building up a full stack quantum processor. All the way at the bottom, we have the devices. This can be made with a variety of different physical platforms. These are just some examples, and there are more candidates coming up as well over time. So it's very exciting on the hardware building aspect. And then on top, I think it's kind of obvious, especially to the audience here, is that we need to build applications and tools that allow us to eventually make something out of these hardware that we're building, right? So, so this part, I think everybody at Horizon or friends of Horizon will be very familiar with. But in between, there actually sits like many sort of mysterious layers of interconnects, control electronics, signal generation and processing, etc. And depending on which hardware platform we choose, be it superconductors or trapped ions or neutral atoms, the intermediate layer will also change accordingly. But in general, the way we can think about them is basically sort of in this kind of flow, right? Like we choose a hardware and then we ask the question, how do we now control them as effectively and as coherently as possible? So this question really brings out the essence of building the intermediate steps, which involves things like cryogenics for superconducting circuits, good vacuum for all the trapped things, lasers for them for control, and microwave electronics for superconducting circuits. Right, so all of these things are very crucial. So the hardware is not really just the devices, because usually I think in popular science writings, these two are kind of what we see, right? The applications and then the quantum chip. But they don't really talk to each other like that. And I think there's many things in between. And this really ties in with a lot of what Horizon is doing, I think, as well, because, for the applications to have good access and good knowledge of the hardware, you need to develop tools and knowledge for people to really tap into that effectively. Okay, and one thing that I think we're currently observing in the industry is that sort of everything above here, we might have access remotely via the cloud, which is very convenient. But there's a lot of things under the hood, and I think if we don't pay attention to them, you could either, cause things to not run as efficiently as they could, or lead us to maybe ignore or overlook certain limitations or shortcomings of the system under the hood. Okay, so this is just a very general overview, and of course, every single step along this chain is very important, and if there's a breakdown in between, it could cause really big failures and mishaps in the system. Okay, so what we focus on as a team is mostly on this layer, and we tap into the current efforts in both academia and industry to really support us in the middle layer, and of course, on top, we'll leave it to the experts to really figure out the interesting things we could do with them. Okay, so now let's zoom in a little bit on the hardware. So I said there are lots of different candidates for building it. They each have their own pros and cons and sort of limitations that we need to overcome in order to make them useful. Right? We specifically focus on this platform called superconducting circuits. And what it is really just electrical circuits cooled down, electrical circuits manipulated in a certain regime such that they exhibit quantum behavior. Okay, so it's pretty straightforward conceptually. And using this kind of circuits, our current view, or actually this is not limited to circuits either, in some sense on the hardware perspective, what we're thinking about right now is, we've roughly tackled the base layer of just building basic ingredients of doing initialization measurements on the single quantum bit level. And now we're at this sort of turning point where we can start to think about building higher levels of the hardware. So one thing that we've heard a lot from various industries is the sort of the NISC approach, so the noisy intermediate regime, where we can build just larger devices based on these base ingredients we've developed so far, and sort of see what we can do with them already, even though they're not yet perfect. Okay, and then in parallel, there are also some of us who are looking a little bit less into scaling, but more into how can we make these individual parts a bit better. But better, we mean to actually perform some sort of algorithms to make them more robust against errors and sort of failures due to environmental interactions. Okay, so both of these are being pursued right now in the field, and I think, you know, at some point they're going to interfere. They're not like two diverging paths. They're really just two steps that's going on at the same time, and eventually we'll tap into the achievements of both to build the robust and universal quantum computer. Okay, so in this talk, in the later part, when I share about what we do, we'll mostly be focusing on this. Okay, so before we go into the details, I'll just do like a quick 2-minute introduction of what are circuits, what are superconducting circuits. So as I mentioned earlier, they are effectively just electrical circuits like capacitors and inductors put together in a regime in a way that allows them to show quantum behavior, right? And the one of the main ingredients is just a resonator or a cavity. Is really as simple as a capacitor and an inductor. How we physically realize them have different ways. We have different ways, but conceptually they're really very much like the standard electrical circuits. And in the quantum regime, they can be modeled as a simple harmonic oscillator. So this is just something with a quadratic potential, and it has discrete energy levels, but they all have degenerate transition energies. Okay. So, you know, for systems like this, you can kind of start to think, okay, now there are discrete transitions. Maybe we can think about putting some information in there in some clever way. Okay. Physically, this can take the form of just a box, really an electromagnetic mode that you can confine the energies in. Okay, the box can have different shapes and sizes, and they're relatively easy to implement. They can also be a strip of metal on a planar surface, so there are really many different ways to implement these. The other ingredient that's slightly less intuitive is called an artificial atom, or in this specific drawing, it's called a transmon. It's a bit of a funny name, but what it is really just still the same kind of element, which is a capacitor, but now instead of being connected to an inductor, it's connected to a nonlinear inductor or a Josephson junction. Okay, so this is one of the simplest nonlinear elements in the basket of ingredients for superconducting circuits. The Josephson junction, its role is really to, you know, shift the energy levels relative to each other such that now the transitions would have distinguishable energies such that you can now address them individually. Okay, so now we can identify them we can name them different things because now we can actually have the ways of selectively asking for some transitions while avoiding others. Okay, and physically they can look something like this, where we have some metal, thin film, very thin metal patterned on the substrate, and inside where this little Josephson junction element just looks like this, which is, you know, and you can see the scale bars here, they're not really tiny as you would imagine, like a single electron or a single photon, but rather they're quite big and you can see it in a microscope. Okay, and the beauty of this is now we actually have a way, you can see these features and they kind of remind us of the good old classical circuits that we do. We print on the circuit board, right? So these things we can fabricate using a lot of the currently available fabrication techniques, and we can kind of engineer exactly the sizes and the shapes and the feature, the patterns and the geometries very precisely to give us the property that we want. And the properties are usually associated with how large the transitions are and what's the shape and depth of the well, etc. Okay, so we have a lot of control over this, and that's one of the advantages that circuits have over, say, some of the other elements, such as trapped ions and neutral atoms, because their properties are very much dictated by their very nature, right? We can still interact with them, but we have a little bit less control, or they have a little bit less engineerability. So this system is relatively versatile, and the base ingredients are fairly straightforward to make. Okay, to make them well, it takes a bit more effort, but to get to an operational level at the moment, I think it's starting to be a much more accessible thing to do. Okay, the next key ingredient is to put these two sort of disparate elements together in some way that gives us capabilities to do manipulations and interactions effectively. Okay, so you can imagine in a circuit, connecting different elements is basically adding a few more elements, which are either inductors, capacitors, or resistors. In this case, the most common way is to just put a capacitor between the two elements, and this actually introduces something called the dispersive coupling. It's a technical term, but physically understanding it is actually quite easy, because all it does is to induce a shift of the frequency, so the gap between the levels, that's dependent on the properties of the other thing that it couples to. Okay, so this is reciprocal. The frequency of this guy shifts as a function of the property of the cavity, and vice versa. Okay, so that's very convenient, because using this very simple coupling mechanism, we can achieve two out of very many other things, but two very important building blocks, which is basically effectively, very efficiently extracting the information about the artificial atoms through the cavity mode. And at the same time, we can also implement sort of operations on this linear mode through the artificial atom. Okay, so these two ingredients actually gives us pretty much everything we need to maybe make interesting states, do some gates on it, as well as to do measurements. Okay, so based on this, we actually have pretty much all the control that's necessary on a single quantum bit level. Okay, so of course, I've been talking about this in a very ideal case. In the real world, if I just put some circuits like this together, they're not just going to become a quantum device right away. I'll have to do a little bit more to them. And this involves the other layers, such as wiring up with filtering, connectivity, whatnot. But the biggest part is really to put them in a nice cryogenic environment. So the main goal of this is to really make sure that all the noise are being frozen out, such that only the desired quantum properties will remain in our system. And thankfully, over the past decade or so, cryogenic technologies have been progressing by leaps and bounds, and now we don't really have to worry about this so much, because we can purchase this commercially. This is the standard image for a dilution refrigerator, which uses some interesting phase transitions of helium-3 and helium-4 to achieve temperatures very reliably to below 20 millikelvin, okay, 10, 20 millikelvin. Okay, and we can maintain this temperature for days, weeks, or months if we wish. So it really gives us a very stable environment for us to perform all these operations and test out these quantum devices. And with this kind of current configuration, which is mostly commercially available on the outside, at the cryogenic part at least, we can fairly easily achieve on a single quantum bit level good fidelities or good quality operations on them. But as we build larger and larger, we'll start to see some deteriorations as well as challenges, which we'll highlight a little bit later. Okay, but this is generally sort of the physical system we have to play with. And I think there's a lot of advantage for this platform, partially because many of these other technologies are available, and they're also useful for other things, like for the microwave signal processing, for example. It's also useful for telecom industry. So there are a lot of existing technologies that we can piggyback on, so that we don't have to build everything from scratch, and that actually really helps us to move forward quite quickly using this platform. Okay, and I guess as a result of moving these technologies and being able to move quite quickly, we have, these days some cloud-based devices that we can have access to. I don't think they opened yet, but this is slightly outdated, but this is the very first, I think, cloud-based quantum processor that IBM opened up to the public. It had 5 physical qubits, so these are the individual qubits, and with their interactions mediated by some cavity modes, which are just linear LC oscillators. And very quickly, different companies announced their different chips and made them available. And you can see the qubit counts have been increasing, which is a good sign. And I think, together with the increasing qubit number, we also need to look into other things like how good are the controls and the gates, right? So both the single physical bit operations and the 2 qubit operations are getting better over time. Still left something to be desired, to be improved on, but they're making progress. This kind of planar structure, they're also quite compact. So these chips are, relatively small in physical dimensions. But as I've shown earlier in the previous slide, you can see that there are lots of other things in the cryogenic and the microwave processing part that has to go with it that are much bulkier, right? So all of these are actually just cables and interconnects and filtering elements, and the actual chip is very small, sitting at the bottom of a fridge, right? So the footprint at the moment is not a limitation, but rather some of these accessories that have to go with it to make them useful. That's relatively bulky. And together with the increased physical qubit count, we now have a larger information capacity, and we can now do some interesting things with it, like with a Google device. They claimed quantum supremacy last year, but more recently, I think they did some more interesting things, like the simulations of Hartree fork, etc. So we're starting to reach a level where these devices, even though they're not perfect, they are starting to outperform classical computers in certain applications. Not very useful ones yet, but still there are examples where we can start to use to show the powers of these quantum devices. And to me, I think these NISQ devices offers this one other really crucial capability now, is for us to learn about the different failure modes of large quantum devices, right? So these are really hard to simulate or dream up on the abstract level. So it's only when we have the hardware to test and to probe, we can start to learn how to make them better, and how to really capture all these different ways that it could fail. Okay, so their roles are very important, even though they're currently not really offering any enhancement in solving, say, a real problem that the industries are facing. Okay, so these are on, I think for the current qubit count, 70 or so is still the highest. And there is a bracket here, I'll mention later as well, is, you can make certain qubits, but the ones that can actually be useful sometimes is fewer than what's actually available physically on the chip, right? So from these, say, 10s to 100 qubit level, maybe the next milestone naturally you would think of is, can we go to, say, 1,000 or thousands of qubits, right? So let's just envision that a little bit, and try to think about what might be the challenges we will face if we use this kind of technology and push it towards, say, 1,000 qubit. Okay, so on the right here, I'm showing like a typical cycle for building sort of a system like this. We'll start, for example, there's all the hardware on the physics side. You start with, say, certain. Let's go top down. So you have an application in mind, and it requires certain Hamiltonian. So number of modes, number of types of coupling, connectivity, and whatnot. And that translates into a certain layout or a design of the system. And then you have to translate that into a real hardware, which involves fabrication. And then once you've made that, we have to characterize it. We have to really figure out, did we make what we wanted to make? Or did we achieve our target parameters? And based on the result of that characterization, it sort of goes back to the design, and then it sort of feeds back into, can we change that to achieve better properties that's more appropriate for our application and whatnot, right? And there's also another step after fabrication that we inspect just on the materials level, on the device, like physical level, did it actually look correct? And this means things like, do we actually have all the right dimensions? Are the precisions good enough? And this also, either is back to the chip design, which sometimes could mean that, okay, if we ask for a certain specification, with the current technology, we're just physically unable to achieve that. So we have to be more tolerant or change our design to make it more accessible for fabrication techniques. Okay? And if everything sort of works out here, what we characterize will become, we can condense that into some sort of metrics. Could be fidelities, could be things like quantum volume, could be circuit depths, different kind of metrics. And then that kind of go back to sort of the resulting Hamiltonian, sort of the target Hamiltonian that we wanted, and we can see if that satisfies what we need. And then if it doesn't, then can we achieve the application or not? And if we are not able to, can we now modify how we construct this application layer to fit better the hardware that we actually have available, given that we've already tried our hardest to build it? Okay, so it's quite it's already quite complicated, lots of arrows jumping around, but it's very much simplified. The actual process has a lot more back and forth between all the different steps. Okay, but you can see it involves many moving parts and many iterations between different parts of the chain. Okay, so just looking at the simplified workflow, we can already identify kind of just naively certain limitations or challenges if we want to push towards 1,000 qubit, right? So first of all, the fabrication step can be challenging because even though we can make single or small devices reliably now, any sort of imperfections that exist on a single or 2 qubit level, once you push towards 1,000, they will be amplified, right? So yield itself could be a problem. So when we're making tens of qubits, very often in the Google case, or some of the IBM devices, for example, even though physically they have, say, n number of qubits on the chip, the ones that they can use could be n minus 5, or I don't know, like a different number. And that's because maybe some of the devices didn't physically achieve the parameters that they wanted, or the performance was not up to par, or there are things like collisions of their frequencies that renders them not very useful. And sometimes physically, we could also face the problem of just some parts of the fabrication not working, right? When you needed an overlap, it's just not there due to some small imperfections in the process. So this happens at a very low percentage these days, like say most of the time, like 99.9% of the time, we get a device that we wanted, at least just on the fabrication level. But imagine if you have 1,000 times that, then the 0.1% of not getting that could become very much amplified, right? So yield could be a problem when we're thinking about building devices, like thousands of them on a monolithic chip. That we're seeing right now. The next thing is characterization itself could be a bottleneck, right? If we don't have a characterization that's effective, then we wouldn't know what we've built, right? We can only build to the extent that we can measure in some sense. If we don't have that feedback, there's no way we can improve on what we've built or even understand what we built. So characterizing, say, tens of qubits, right now it's relatively well understood. It still takes some time, but going to thousands of qubits, what we'll need here is we both need basic speed as well as accuracy. Right? So we need to characterize individual ones or some of the groups of them, sometimes together, for their collective action or interaction with each other. And we're also running against the clock because if we take a long time to characterize, by the time we finish characterizing the last set of qubits, then the first set might have moved due to some global events, such as radiation and things like that, that their characteristics might have changed. Okay, so there's quite a lot of restrictions, or rather targets we have to meet in order to make the characterization actually useful for our system or for our feedback process. Okay, and finally, the application layer that sits right on top, it's not easy to do as well, because we have to really rethink how we want to construct our tasks that can take advantage of these quantum behaviors. Right? It's not as simple as just doing a translation from one code to another. Is really rethinking what kind of new algorithms we can come up with that will make full use of the additional capabilities that quantum hardware could offer, in contrast to what we can do with classical systems. So these are quite a lot of challenges, as you can see, just from a naive view, right? So, but you know, it may sound a little pessimistic, but I think there are lots of different efforts from various different fields. It's becoming more interdisciplinary as well, that are really trying to resolve these challenges. So it's definitely not hopeless. We're making progress on each of these fronts. And I think it would take some time for us to really get to the level where the whole process works very effectively and holistically together. But these are active research areas still at the moment. And I think, you know, we're not quite at the level where we can say now we can reproduce or we can reliably make qubits, at least on thousands of qubits level for quantum hardware yet. And this is, I think, a general statement for quite a lot of platforms that we have, yeah, not just for circuits. Okay, so in view of these challenges, I think the alternative, while we're making progress and making new research sort of to tackle them, it also warrants sort of, you know, thinking a little bit out of the box and try to think about how we can maybe, you know, instead of using brute force to really build larger and larger device on a single chip, can we do something slightly different? And this sort of goes back to my, say, second slide, where I said there are, like, you know, two parallel paths right now where we're also studying, you know, maybe smaller things, but do something that makes them more robust on the individual level first. Okay, and this calls for quantum error correction. And what that means is really just to say that on each of these small chip level, we do something such that individually they're very robust, and then you reproduce these individually robust things in a certain way, such that maybe you can avoid some of these, you know, really potentially really challenging bottlenecks that we might face. Okay, so just very briefly, quantum error correction is basically basically requires us to spread your one bit of quantum information into several different physical elements. Okay, and in order to make this useful or make this work, very often we'll need to have both individual control of the elements that you spread into, as well as interactions between the two of them, or even multiple of them. So with these, what we could do is that if something happens, so in this case, this is the state that we want, but if something happened, with this redundancy, we can now correct it without destroying our state. Okay, so we have this a little bit of buffering in this simple example to protect us against one specific type of error that would happen. And a very, I think, useful concept to think about is that when is quantum error correction actually useful? Right? And this is what we call the break-even point in the field, which is really just saying that I'm doing all of these additional efforts, right? I added redundancy instead of one thing, now I have many things. It doesn't sound good in the beginning because now you need more control, more measurements, more gates, so there's some overhead associated with it, right? It's only when all of these overhead sort of are actually actually stops imposing a penalty so high that quantum error correction becomes useful, right? So this break-even point is really just to say that we can actually gain some extension in the lifetime, in how long we can preserve this information by doing more. Okay, and this is actually a very hard thing to achieve because of these extra work we have to do and all the penalties that they impose on our system. So how do we do that? Well, there are a few different ways. Two of the most prominent ones is sort of into, you know, basket of things. One is using discrete systems. So here I have sort of three things, each have two possible levels. And I say, this is what I want to use to spread out my information. And I want to do gates and controls between them such that I can implement some algorithms to protect this information. The problem with this is that with every additional element, so for example, each of these additional ones, I add more channels of errors happening, right? And I also add things that could be hard to correct, which is sort of interactions that are not wanted, that are unwanted between them. So even though this is relatively easy to test out in our current hardware because we have systems with tens of these discrete systems, discrete elements already, it can be really hard to achieve this break-even metric that we think is useful. So yeah, the overhead is pretty high in general. The alternative is to use, say, a single hardware. In this case, is a cavity that we've met earlier, and use different levels of it, right? So conceptually, is maybe not so different, right? Because here we're adding more levels. This is one transition, another one, and another one. So here you can imagine if I have some way to individually manipulate them, then I have different transitions that's available within one single hardware as well. So that's naturally a little bit more efficient in terms of just building things and also in terms of introducing additional errors, right? So this is what we call a more hardware efficient approach because we're gaining in these accessible levels without adding too much overhead in the control and in the errors. Okay, so so I think this kind of approach, the one that uses a linear mode, is a continuous linear mode, is been around. This idea has been around for quite a while, and then the experimental realization really started to show up over the past, say, 7-8 years or so, and it's been making quite a lot of progress since then. Right? So a simple roadmap for that would be, say, can we use this kind of system to encode just one logical, so one protected bit of information, such that we can actually extend its lifetime. And then we want to do all the possible gates that we need on this protected information. And then we want to now build several of them in exactly the same way, but find another clever method to introduce some gates between them. Okay? And then finally, if we group lots of them together, then maybe we can build a network of them such that we can have fault-tolerant quantum computing. Okay, so I think we're making pretty good progress on these first two, and it's more and more work showing up in this next jump. And we do have a good idea on what might allow us to make the final leap towards the building into the construction into the larger fault-tolerant quantum computer. And in a very cartoon kind of way, you can think about that as basically just building individual elements that are corrected and that has control on them, right? And then link them up in some sort of on-demand communication channel. So this is very much modular, right? So you can turn them on and off, for example, or you can change their connectivity in a more flexible way. So this is in contrast to a monolithic chip that we were currently seeing for NICs devices. Okay, so it's a slightly different architecture, but it's actually, not so unfamiliar because this kind of modular architectures exist in nature a lot. Yeah, sorry. Yeah, so in a lot of classical systems, when we need a lot of complexity and scale, we kind of build them in a modular way, right? We don't build billion-dollar systems in one giant box and not having individual troubleshooting and control over them. So what we're doing is very much the same, recycling these ideas and say, okay, for quantum systems, we know they're hard to build, so let's build them individually and then connect them later, such that if there's something happening, we could have some way of not throwing away the entire expensive hardware, right? So in a sort of very naive way, you can think about building smaller chips or smaller quantum units and wire them up. But each of these communication or connectivity channels will have so they're on demand, so they kind of have a switch between them. So if one of them fails, right, I can take that out of my network of modular devices and preserve the rest of the system without being affected by this individual failure, okay? And the individual protections can happen using the quantum error correction, using standard quantum error correction techniques, okay? And without going into too much details of what the quantum error correction techniques are in this kind of platform, I will just briefly show some general overview, right? So using this kind of systems, which is the single mode, but many different levels, kind of cavities, we can really use different symmetry properties to encode the information. Okay, so this is a very simple example where we're just saying, okay, all the even transitions is one state or one logical state, and all the odd ones would be another, could represent another. Okay, this state actually has a name. This kind of states can be called cat states, or basically coherent superpositions of different states. And they're fairly easy to construct these days because we have good control on these single modes. And we also have flexibility on exactly what kind of superposition to what weight and what kind of phases, relative phases we put, right? So with this architecture, or with this quantum error correction technique, we have access to roughly 3 types of codes. You can see that they're all using some sort of symmetry properties, and they actually gives us different types of protection. Okay, and that flexibility is important. So for example, based on the hardware that we have and the noise that we have in the environment associated with that particular module, we can choose which type of encoding we use without having to change the system physically. Okay, so we can have that device ready, we can change the encoding on the fly in a programmable way, depending on, say, the noise model that we recently characterized and discovered. Okay, so that kind of the availability of different types of encodings in such systems is a very useful thing, and I think the different kind of enhancements or protection that they offer could also give us some really useful boost in special configurations where the noise model is very different in certain parts of our modular network compared to the other, right? So we're not locked into a certain fixed quantum error correction scheme. Okay, so with that, let's just go back to this cartoon view again, right? Imagine I have individual connection and this kind of on-demand connectivity ready, and I also have the flexible encoding that I can choose individually what I want to, how I want to encode. And then, in principle, I would have a network of these modules that will give me quite a lot of computational power, right? So that's nice. So physically, how do we do that? Currently, a lot of these individual modules with quantum error correction looks a little bit like this. Right? They're kind of bulky, you can see, but they're right now at the proof of principle levels to really show that we can do it indeed, and we can achieve all these targets that we want. So this is basically a physical implementation of those cavity modes that I talked about. There are 2 of them in here, and here it's a chip containing a nonlinear artificial atom, which we introduced earlier. Okay, so with this kind of hardware, we can build modular networks like this. We can also do some other interesting things. So just briefly mention that this is sort of a follow-up work from my PhD that some of my teammates did, which is basically using the same device, but now manipulate it in a different way such that you can actually very effectively simulate some molecules in nature and their spectrums. Okay, so this actually gives us, in some sense, some like really broad range of explorations that we can do with very similar hardware constructions. So, for now, since things are bulky, you may not be able to see how this can really all fit into this dilution refrigerator I mentioned earlier, or how it can really go into tens of thousands of individual modules. But what I want to point out is that the current implementation are not specific to this concept or this architecture at all, right? We can realize the same modes and the same controls in a very different way. So for example, this is a much more compact and familiar looking structure, right? It has many layers, and each layer can be patterned to have modes such as a cavity and control lines, and the next layer could have these nonlinear artificial atoms, right? So this is still sort of a visionary picture from 2015 or 16, but the realization of this kind of more compact chip type of structures that will reproduce all the features that I've talked about, which is the large information capacity, good quantum error correction, as well as encoding, without really sacrificing anything. Right? So I think the latest results from Yale and Lincoln Labs have shown that you can make cavities using this kind of very small footprint lithographically designed patterns with lifetimes up to milliseconds. So this is already incomparable, very much comparable to the big bulky architecture I've shown earlier. Right? So all the tools we're developing now using these bulky things can be translated into these much more compact platforms once they are ready to be deployed. Okay, so there's the physical dimension right now is definitely not a limitation, and I think there's a clear map for how we scale this up eventually when physical footprint might become a constraint. Okay, so just before I end, I think I just want to mention a little bit about all the other things which I talked about in the beginning as well, right? It's not just the hardware that we need. There's also all the other things like electronics, the dilution refrigerator, all the control lines interconnects, and we also need people who are able to, think about it both on a classical level in terms of programming and information processing, as well as, understanding the hardware and knowing what to do with them. Okay, so it's really sort of the infrastructure needs to be there for us to do meaningful experiments on these and to continue to make progress. For my team, I think we want to focus on quite a lot of different things going forward. Of course, the primary goal is to try to build, a system consisting of a few of these modules, each individually protected against errors, and then see if we can do, higher level correction or do gates between them to make them small test beds for algorithms that's compatible with our platform. We can also look into things such as, new physics. This is a funny state where you can have a superposition of two discrete states, and this kind of states could offer really new information about how entanglement works, what are the different signatures you can extract from different systems that are entangled to each other. There are also new models. I think Jane is probably familiar with this. This is sort of after talking to Millie, there might be some projects in the future on testing out some of these complex models that our theorist friends are constructing in our architecture that could be a useful test bed, right? And where we are now is, I think, so I started officially last March, probably exactly a year from now, a year ago. So it was quite empty when I started, but thankfully with a lot of help from the university and all the different suppliers, we now have our main tools up and ready. So these are our control electronics, and this is our small dilution refrigerator. We have a team of about 7 to 8 people that's, from students to research fellows to that are sort of learning and getting ready to start building something soon. Okay, so we're still in the construction stage, still thinking about plumbing a lot right now, but hopefully in another three months or so, we'll be actually at the stage where we can do something interesting with our systems. Okay, I think that's the end of my presentation. Thank you very much.
Thanks very much.
Are we doing questions or?
Sure, I think.
Okay.
I have a bunch of naive ones. The second last slide, it looks like you can entangle multiple of these chips simultaneously.
Yes.
Yeah.
So like.
I'm only looking at the big theory picture, thinking I should go to the second last slide. The one with big U.
Oh, this one.
Yeah, it looks like you can entangle an arbitrarily large number of these modules simultaneously.
Arbitrary, maybe not yet, but yeah, the goal is to construct these large unitaries. One thing I skipped over is maybe like as a testbed architecture, we're going to try. We might make something like this that's quite relatively simple to make and it's still modular, so we can replace individual elements, easily to get the right parameters. But in something like this, we're thinking maybe 4 to 5 bosonic modes with some sort of nonlinear intermediary that could induce this kind of nonlinear coupling. The good thing with these is that basically all of the couplings are programmable, so they're not built into the hardware, they're driven by microwave, so we can sort of play on the outside without changing the hardware itself.
And each one will sit in the same chip, basically.
Sorry?
Are they all embedded into the same chip, or are they all embedded separately and they're actually networked with the wires?
So I think they are going to be individual chips, but still embedded in some sort of 3D enclosures. So a bit of a hybrid between the fully planar and the fully 3D things. Yeah. So, but this is really sort of an intermediate step in the sense that we're getting more flexibility with and sort of convenience with architectures like this, but their performance is not going to be as good as the fully 3D one or the latest patterned ones. Not right away, but their connectivity would be better. So what we want to develop is, say, like new gates or new entangling operations between them, while waiting for the fab to get better, so that we can transition over to the more robust fabrication platform.
So that's pretty cool.
Yeah.
And also, your second last slide looked like you're going to build GKP states.
Yes.
Oh wow.
So, so actually, I skipped this over because so the GKP states were created in one of these cavities, right? So they can be created in basically any linear modes with a nonlinear ancilla with the same techniques. So yes, like we can create GKP states deterministically, and we can use them as our first layer quantum error correction if that's the goal of the investigation. Yeah. Yes.
So. On this staircase here, when I think of doing universal control, usually I think of multiple qubit operations as being a prerequisite for this.
Mm-hmm.
So I would have switched the green and blue bars, but you have like a trick that allows you to do universal one qubit operations without having to do any distillation or anything more complex.
Yeah, so I guess the individual one qubit operation for us it's easy because it's one piece of hardware, so it's a single mode control.
Well, okay, so how do you retain fault tolerance while having universal control?
Yes, so this I don't have a slide for this, but this can be done. So okay, currently there is a cheap and dirty way to do universal control without fault tolerance, right? Yes, but to maintain fault tolerance or at least achieve break even, which is sort of a thing that I wanted to mention here. I mentioned here is we have some techniques. So for here, we're not quite yet doing sort of fault tolerant, but we can almost achieve break even on the single qubit, on the single logical qubit level. So what that means is that you do operations on this protected qubit, and then you compare to do in a way that's supposed to be more robust in error, and you compare to just doing in a naive way. So we're starting to get to a level where this is becoming actually useful, the tricks that we're implementing.
You get the same single qubit logical error rate that you would have at the physical level.
Yes.
Ah, okay.
Right. So not yet fault tolerant, but at least extending the logical lifetime while doing gates as well. The next step will be a little bit harder, right, to achieve break even in multi-qubit operations. This is still taking some time, but...
I mean, if you can inject magic states with your one qubit gate error rate, then that's better than what you could do with a multi-qubit code.
Sure.
You have to suffer the 2 qubit error rate.
Yeah, but I think what might happen is that there will be a second step, or rather, like, put this all in a box and then put to a higher layer, right? So now we have individual and 2 logical qubit control on just achieving break even, but not fault tolerant. Right, and then you can do a next layer, maybe with surface code or what other things that people dream up. Then the next layer will have have an easier time to reach their threshold that's necessary to achieve fault tolerance. Yeah, so there will be concatenation potentially. I mean, most likely there will be. In what form? I think that's right now very much at the forefront. Yeah, cool.
Any other questions? Well, in that case, let's thank Yvonne Y Gao.
Yay, thank you.